Okay, so we're going to record this as well, and I'll put it up. I'll put it up online. So this is just, the quickie review of Chapter 10. Remember, Chapter 10 is all about simple harmonic motion. If something's in simple harmonic motion, it must be moving. So if you think about the SHM activity we did, the very last thing, that when you did Hooke's Law, was anything moving during Hooke's Law? When you used the second part? No, it's just hanging there. So pay attention to what's going on. And that's one of the reasons I like that activity, is to kind of help you remember that if it's moving, you get this sine wave and the force doesn't stay the same. I had, not in this class as much, but in my other class, I had a bunch of people trying to read the x off the graph to figure out the force and do F equals kx of Hooke's Law from the graph, and it doesn't work because the force keeps changing, right? The further away you are, the more force you have. So pay attention if it's moving. So it needs a restoring force. That's why bouncing a ball does not count as simple harmonic motion. Only pendulums, springs, circles, things that are being pulled back to their center. Our basic equations, these ones you do not have to use. These are the ones I think make life so much easier if you can remember them. But they're not on your equation sheet, and they're not expected that you know them, but you're allowed to use them because they come from Chapter 8 and 9. Right? So x is equal to a cosine omega t. So that means that your x max is a. That makes sense, right? The maximum x displacement you're going to have is the amplitude. That's why when you looked at the sine wave, we're going to get more into waves in our next chapter. When you looked at the sine wave, you figured out the amplitude was at the top, which is what the x was at that point. V is equal to negative a omega sine omega t. And so the maximum is going to be a omega. And 90% of the time, you guys only care about the max. You really hardly, I don't think I give you any problems where you have to worry about it in a certain place. There's maybe one, but you can use the energy equation to figure it out, which is probably easier than this one, unless you can remember that equation. And then a is equal to negative a omega squared, cosine omega t, so the maximum is a omega squared. That's centripetal acceleration, right? That should look exactly like centripetal acceleration, no different. That's taking an omega and just changing it to translational velocity. So, I mean, you've seen these before. So that's why I like these equations. They kind of bridge the gap between Chapter 8, 9, and Chapter 10. And it works for circles, it works for springs, and it works for pendulums. So simple harmonic motion, as long as there's a restoring force, you can think of whichever one you want, and all the equations will work. Because sometimes it's easier to think of the spring, sometimes it's easier to think of the pendulum, whatever works in your head, right, to be able to figure it out. Everybody, we still got a few people writing. There's not a ton in this chapter. There's not a ton in this chapter, which makes it nice in some ways. I haven't actually created the test, but my plan right now is probably 3 free response questions and probably 10 multiple choice. Probably 3.
That sounds like
at the most 4, but probably 3. Well, because remember last time you guys ran out of time when I did. And last time the problem was there was so much stuff it was hard to find 3 that covered everything. This time I think I can find 3 that pretty much, something on simple harmonic motion, something on hooks, and something on energy. We're good.
Last time did you intentionally give us more time on the multiple choice than the free response?
I can give you more.
Yeah, you did.
We had like 35 minutes.
We had 35 minutes.
Multiple choice and like 15.
We only got 20 minutes.
Oh.
Curve would be nice.
I did curve it. I curved it very nice. Hooke's Law. Hooke's Law was the part 2 of that SHM activity where it's not moving. F equals negative kx. Is that negative important? No, it's really not. All it's telling you is that when you pull the spring this way, it's pulling it back. If you pull the spring the other way, it's pushing it back. It's just if the pendulum goes one way, gravity pulls it back to the center. It goes the other way, pulls it back to the center. It's always opposite the way it's moving. X is the displacement from equilibrium. I hope you figured out now how to find that. Remember the very first activity, most of you measured it wrong with the ruler. So make sure you understand when you read the problem where it starts and where it ends. K is constant. Now this part I didn't emphasize, but I need to make sure you understand this. Is that if you cut the spring in half, it gets stiffer, and it gets stiffer by the. So if I cut it in half, it's going to get 2 times bigger. The K. If I cut it in thirds, it'll get 3 times bigger, right? Because the number of coils actually determines how stiff it is. And I don't think I pointed that out, so I want to make sure that was in the review notes. If an object says it behaves as a spring, you can use the equation F equals kx, so it doesn't have to be a spring. right? It could be a rubber band. It could be a piece of elastic. Anything that it claims works like a spring is fine. It doesn't work if the object spring becomes deformed. So if you look at some of my springs, sometimes they get too stretched, and once they get too stretched, yes, they saw that, they don't act the same, right? So Hooke's law is nice and linear, and then you get to a certain point where it just is no longer linear because you've basically messed up the spring. Tiana, do you have a question?
Can you explain how when it's cut in one half?
So if I took a spring, right? If I took a spring, and let's say it's K. My board is being really slow. Let's say the K is 2, right? And then I cut it in half. So I cut it in half. So it's half. And so now I have 2 springs. Each spring is going to have a K of 2 times 2, so it's going to be 4. And if I cut it in 3 parts, right? If I cut it in 3, so I have 1, 2, 3, then it's going to be 3 times 2, so it's going to be 6 newtons per meter squared. Right? They're all newtons per meter squared. So every time I cut it, it gets stiffer. That same amount. And that was one thing I didn't think I pointed out. Everybody good? What's up? Okay. So periods and frequencies. I was a little disappointed that there was more than one group that couldn't remember this. This is very important. So you realize, right? Because you had to find T on your graph, and then you had to convert it to frequency. And for a lot of people, that just was like, huh? And so remember, T and F are inverses of each other. So if you have one or the other. This is F in, what's the unit for F in this one? This is hertz. Right? My slow board today? That's hertz. And what would this be in? What's omega in? Radians per second. Right? So they're all the same thing. They all represent the same thing. F and omega are exactly the same except for a 2 pi conversion. T and F, T and omega are just inverses of each other. One with a 2 pi conversion in there. So if we're dealing with a pendulum, then T is equal to 2 pi square root L over G. Right? You should know that equation. It's on your equation sheet, but you should be very comfortable with that equation by now. And more L means there's more time. For a spring, T is equal to the square root of 2 pi square root of M over K. More M, more time, more K. I don't know what happened to K. More K, less time, right? Because it's going to be springier. So it takes less time to go like that. Both those equations are on your equation sheet. One's labeled TP and one's labeled TS. So one's period of a pendulum and one's period of a spring. Okay. And then over here in the box, I might have to go up and down a couple times. Over here in the box it says if you force an object, if you force an object to vibrate at its natural frequency, it will resonate. Oh wow, won't let me get rid of that. That is weird. Okay, it is definitely second period, Kellyanne.
I know.
There. Now, if you force, oh my goodness. If you force an object, this was one of the concept questions. That was the person going over the bumps on the road, right? If you force an object to vibrate at its natural frequency, it will resonate and it'll make a really big amplitude, right? So you'll bounce a lot. And the best way I think to think of that is with swings. So if you're swinging and you're pushing somebody on a swing and you push them at their natural frequency, they're going to go really high. But if you kind of push them out of sequence, right? You don't stay with them, then you just mess up the swinging, right? And they don't go any higher. That's called resonation. And we're going to talk more about resonance in the next chapter. So it's kind of like is leading into that next chapter. I see people still writing, so I'm waiting. Good? Okay, conservation of energy is the next big topic. This is really important, guys, and we only did a little bit of it, so make sure that it makes sense. but it's the total energy is equal to 1/2 Ka squared. And so energy at the equilibrium in the center is all kinetic energy, so it's 1/2 mv squared. So at any given time, you can use this equation, right? 1/2 Ka squared equals 1/2 mv squared plus mgh. If, let's say it's doing this, let's say you pulled the spring, right? I pulled the spring. In the beginning, all of its energy is 1/2 Ka squared. So I would say, oh, then at some point in time, that's all true. And I just set that equal to 1/2 Ka squared. So I pulled it to 3 centimeters. I know the K. I know how much energy I have, right? At 2 centimeters, and let's say it's not going up and down, so that goes away. At 2 centimeters, how fast is it going? Right? And you can figure out the velocity. Just beware that this A and this X is from equilibrium. They love to give you problems where they say the spring is like 1 centimeter and then it gets pulled to 1.1 centimeter. So everybody decides that A is 1.1. But A is really 0.1, right? Because it's the difference between where it started. So make sure you read it carefully. Because like I said, I'm going to give you one's going to be on springs, one's going to be on pendulums, and one's going to be on energy. I mean, that's kind of the easiest way to do the free response. Oh, well, I might do the bulk stuff just as a multiple choice. Because that's the only one. So many times what happens as it's moving, right? If it moves, and you don't, this is a picture straight from your notes. You can copy it if you want, but it's not as big a deal. As it's moving back and forth, if I pull it to its maximum and it reaches equilibrium in the center, then 1/2 Ka squared equals 1/2 mv squared. It's like the person jumping off the cliff, right? mgh equals 1/2 mv squared. It's just as a spring, so 1/2 Ka squared equals 1/2 mv squared, right? And then it goes back to 1/2 Ka squared. You only have to use this one if you're somewhere in between, not in the center and not at the ends, right? So this is at the end, and this is in the center. Right? So it goes from end to center, end to center, end to center. Yes?
Is it like that because the whole like kx naught plus 1/2 n naught squared, but like a lot of things equal out to 0? So
Yes, so everything goes to 0, exactly. So this becomes 0 because x is now 0 because it's in the center. And it didn't go up and down, so that's 0. So the only thing left is...
So if it started already non-equilibrium and went even farther, it would be a whole different equation.
Well, they're not going to, you have to start somewhere. So they usually start either with it uncompressed, and then something squishes it, right? So it could go the opposite way. It could be, it starts at a speed, right? So something comes, real common one is like a marble comes and hits the spring, right? And squishes the spring. You're going to see that in the worksheet you do tomorrow. And it squishes the spring, and so you know the velocity, 1/2 mv squared, has to equal 1/2 Ka squared, because all the energy went to compressing the spring. Right? But it's real common that that's what you end up. When you did your activity, you guys started with it compressed, and then you had to turn into kinetic energy. Right? That's what we did in that activity. Okay? Because that's real common. Good? So the last thing, see, I told this chapter's short. What, it took me 15 minutes to do the whole review? Get that? So elasticity, there will be questions on elasticity. It might be multiple choice. I haven't decided yet. If that would be the fourth question, that would be the fourth question on elasticity. And so stress is F over A or P. Remember the difference between these two, F over A, it's either parallel or perpendicular to it. And for pressure, it's all the way around. Strain is how much it changes, so delta L per L naught, or delta X per L naught, or delta V per V naught, so how much it changes by. So linear deformation, you use Young's modulus, so that's Young's modulus. If it's shear, right, it's parallel to it, so with Young's, you're pulling like that. With shear, you're pulling like that. That's the difference, right? And this is the shear modulus. So it's the same equation, F over A equals S delta X over L naught. And then for bulk, it's just pressure. So this is the bulk modulus. And that one, there's not really a picture to draw. It's pretty obvious when it's bulk because it's like a balloon or a box or something that's getting squished all the way around. And P totally surrounds it.